Continuing on with chapter 13, let's take a look at section 3, tangent lines and derivatives. Now, the word tangent should sound familiar to you, but again, it's a useful word. It has several different definitions. If we go back to our geometric, not the trigonometric, the geometric definition, a tangent line is a line that touches a curve at exactly one point. Okay. Now in geometry, we talked about a line that was tangent to a circle. That point of tangency then would create a 90-degree angle with the radius to that point of tangency. But now we're taking it a step or 28 further and talking about a line that is tangent to any kind of curve. In figure 1, for example, shows a line in red, T, that is tangent to a standard parabola with, hey, look at that, the simple equation, y is equal to x squared. We have the tangent line that touches the parabola at the point 1, 1. Well, what do we know? What do we like to measure when it comes to lines? We would like to know the slope. But hold on, if we have just the coordinates of a single point, it's kind of hard to use the slope formula when you don't have that second point. We know 2 points determine a line, and right now we have the coordinates of but one. Whatever shall we do? Pick a different line. Okay, so if we're going to pick, now again, it's kind of hard to see here if you stare at that maybe a little bit more closely. That blue line going through point P, just like the red line does. But we're going to pick another point on our curve, on our parabola in this case, and call that point Q. And again, since it's on the parabola, it's going to have coordinates x, comma, x squared. If we play connect the dots between point P and point Q, that is not a tangent line. A line that intersects a curve, such as a circle from before, or a parabola, like you see here, is called a secant line. Now that we have 2 points there for the blue line, we could go through and calculate what the slope is. Okay, and again, we remember our lovely slope formula. So for the slope of line PQ, we're going to take the difference in the y coordinates. Again, point Q has coordinates x, comma, x squared. P is at the point 1, 1, so your difference in your y's will be y squared minus 1. The difference in the x's will be x minus 1. Where do you put point Q? Now you note there in figure 3, starting on the far left, if we put point Q so it's not, relatively speaking, close to point P, we're going to get a particular slope for the blue line. All right, it's going to be positive, which is, again, the same thing we can say for the red line there. But then look at the middle figure. If we put point Q a little bit closer to point P, the slope of the blue line gets closer to the slope of the red line. For the third one there, on the far right, put point Q even closer to point P. Well, the slope of that blue line is getting closer and closer to the slope of our red tangent line. We can even go here, put point Q way over there, somewhere on the left. Now, hold on, the blue line now has a negative slope, and the red tangent line is positive. But then we move point Q a bit closer to point P. So it switches now from a negative to a positive slope. And we put point Q closer and closer and closer to point P. The slope of the blue secant line is going to get closer and closer to the slope of the red tangent line. So we could say, The slope of the tangent line is the limit of the slopes of those secant lines as Q approaches P. Doesn't matter if we come from the right or to the left, it should be consistent. The limit should exist. Well, it's time for some algebra. So again, using our slope of the secant line, we're looking at the limit as x approaches 1. Again, we're going through the point 1, 1 on the parabola for our tangent line. We have x squared minus 1 over x minus 1. Factor that numerator, x plus 1 times x minus 1. Oh, look, we have common factors. Reduce those down. We don't have a denominator that could potentially be 0 anymore. We can do the straight substitution. 1 plus 1 is 2. The limit of this function as x approaches 1 is 2. So that tells us the slope of the tangent line is 2. Now that we've got the slope of the tangent line, we can take that and put it into point slope formula. Y minus y sub 1. Again, the y coordinate of our point of tangency was positive 1, is equal to m, the slope we just found was 2, times the quantity x minus x sub 1. Again, the x coordinate of our point of tangency was also 1. Do a little distribution, combine like terms, put it in slope-intercept form. Y equals 2x minus 1 is the slope of the tangent line. Sometimes, again, the slope of the line tangent to the curve at this particular point is an awful big mouthful. Sometimes we refer to the slope of the tangent line to the curve at a point as simply the slope of the curve at that point. Okay, again, a curve doesn't technically have a slope. This is just a shorthand version of it there. So then we get, oh, does that look somewhat familiar there? Down at the bottom is basically just trying to come up with a formula, I guess, expressing this, the slope of line PQ. We're going to take f of x minus f of a divided by x minus a. Again, a is going to be a particular value, what the x coordinate is at our point of tangency. So again, they give you all kinds of lovely, this works for any kind of a curve. It doesn't just work for parabolas. We've got that point P where we want to know the slope of the tangent line. Put point Q someplace else on that curve. And as Q approaches P, the slope of that blue secant line gets closer and closer. The limit approaches the slope of the tangent line. So here's our first definition of a tangent line. There's another one to come, and there's a couple of interpretations to come. Again, provided the limit exists. Okay, let's use it. Find the equation of the tangent line to the hyperbola. You guys remember hyperbolas, right? The hyperbola, given the equation, y is equal to 3 over x at the point 3, 1. So f of x is 3 over x. The slope of the tangent line at the point 3, 1 is, all right, so we're going to use our definition of the slope of a tangent line. We're going to take f of x, which is, again, the f of x here, we're just going to substitute in the function 3 over x minus f of 3. Well, if you want to go ahead and put 3 in here, but they told you f of 3 is basically the y coordinate of our point of tangency, so that's 1 over x minus a. Well, in this case, a is 3, so it's x minus 3. Now, all right, forget about the fact that it's a limit as x approaches 3 for a moment. This expression here needs some work. So we could go through, yay, we love fractions inside fractions. All fractions are complex. No, this is called a complex fraction here. Again, that is implied to have a denominator of 1. Here's a 1. Here's a 1. This is an x. If we multiply everything by what would be the common denominator of all four of those terms, that would give us 3 over x times x is just 3. 1 over 1 times x is going to be minus x. And note how they left the denominator in its factored form. They didn't distribute there. Okay? Because now look at what happens. Here in the numerator, we have 3 minus x. Inside the parentheses, my denominator says x minus 3. Right number of terms, right values, wrong signs. So if I say take that numerator there and factor out a negative 1, then we get an identical factor with our denominator of x minus 3 that we can reduce. Oops, they used the word cancel. Don't tell Mrs. Keller. So it gives us negative 1 up top. It gives us an x at the bottom. Now, if we try and use our definition of a limit and substitute 3 in place of x, do we get a 0 in our denominator? No, we don't. We can substitute the limit as x approaches 3 of this function should be negative 1/3. And again, remember our interpretation here. That's the slope of the tangent line at that point. So again, take this, put it in point slope form, and then I'm guessing because you guys just like fractions so much, they decided to put it in this alternative form here. I don't really understand. You could have just put that in slope intercept form and that'd be fine. So be careful with the answer key, what Bob is going to tell you here. I'm not sure if they put all of the slope of the tangent lines in slope intercept form. So be careful when you're checking. And then for those of you that need the visual, here in blue is our hyperbola where y is equal to 3 over x, where both the x-axis and the y-axis become the asymptotes, centered at 0, 0. Here's the point 3, 1, and there in red is our lovely tangent line. Okay, another way that we can talk about the slope of the tangent line is using, oh, we love fractions so much. Instead of two terms, x minus a for your denominator, let's do a little bit of algebraic substitution. Let's let h be equal to the expression x minus a. So our denominator here, instead of x minus a, becomes a single term h. But wait, hold on. If we're doing this substitution, then our value for x, do the algebra there, x has to be a plus h. So instead of f of x minus f of a over x minus a, this now becomes f of a plus h minus f of a over just h. Okay. Now that should look somewhat familiar. You did a problem earlier in this chapter where this was the form that you had to simplify. And they even give you a sneak preview of this. There was one of the problems I assigned to you from chapter 12 that had this particular form. Okay, so this leads us to our next definition of a tangent. The slope of that tangent line is the limit as, oh, notice how this has changed now, as h approaches 0. Back here, we have the limit as x approaches a. Here, we have the limit as h approaches 0. And again, it was f of x minus f of a over x minus a, but we did that algebraic substitution, so now it's f of a plus h minus f of a all over just h. Again, h is x minus a. So let's try our new definition. Find equation of a tangent line to the curve y is equal to x cubed minus 2x plus 3 at the point 1 comma 2. All right, so now we have a cubic function here, and the slope of the tangent line at that point, we really don't need to go through the process of trying to graph that. Now, if you want, yay, graphing calculators, you can type that in. That's not too tough. What I really want you to focus here is on our new definition, okay? So f of x is our function x cubed minus 2x plus 3. A, in this case, is 1. So we need the limit as h approaches 0 of f of 1 plus h minus f of 1 divided by h. So for this first part here, we now have a binomial f of 1 plus h. We've got to substitute that in place of the x in both, in this case, two places. So 1 plus h cubed minus 2 times 1 plus h plus 3. So all of this in that first set of brackets there is f of 1 plus h. And then we have to subtract f of 1. So we're going to take the number 1 and substitute it for x into that entire function. So 1 cubed minus 2 times 1 plus 3. And again, it's all divided by h. Now that numerator needs some help. So again, do you remember our binomial theorem? 1 plus h cubed should give us 1 plus 3h plus 3h squared plus h cubed. If not, you might need to go back and review that binomial theorem. Then we distribute negative 2 times 1 and negative 2 times h. That'll give us our next two terms, negative 2 minus 2h. And then 1 cubed minus 2 times 1 plus 3. That should simplify into a constant value there of 2. All right, so now we take a look at the constant terms. We have positive 1, minus 2, plus 3, minus 2. Hey, what do you know? That gives us a sum of 0. Isn't that convenient? And then again, like terms, 3h minus 2h will leave us with positive 1h. They didn't even bother putting this in proper order because they're just kind of leaving it in the same sequence they had up here to hopefully minimize confusion. There's only one h squared term. There's only one h cubed term. This is what you should always be able to find out. Just combining like terms here. In the numerator, h should be a common factor that you can take out and they just, simplify and cancel h. Thanks. Divide. H divided by h is 1. 3h squared divided by h is 3h. H cubed divided by h will knock that down to h squared. No more 0 in the denominator. We can apply our definition here of a limit as h approaches 0. 3 times 0, 0 squared. This limit is equal to 1. And remember, this limit tells us the slope of the tangent line. So that goes here into our lovely little formula, point slope formula. Simplify it. This time they did decide to put it in slope intercept. The equation of the tangent line to that cubic curve at that point is y equals x plus 1. Here's a very, very popular topic when it comes to the calculus, derivatives. Look at the formula. This is just another term that we have for the limit as h approaches 0 of that exact same thing we just practiced there with example number 2. But we're giving it a different name now. That value of the limit is called a derivative. Now you'll note here, again, this is really subtle notation. That little slash mark there, it almost looks like an apostrophe, but You don't have to make it curvy or anything. Just that little slash mark there. That's our notation for the derivative, if the limit exists. Okay? Finding a derivative at a point. So here's a new function, 5x squared plus 3x minus 1. Find the derivative of the function at the number 2. Okay, so we're going to simply go ahead and use our old definition with the new name, the definition of a derivative, a is equal to 2. Notice we've taken out the whole finding slope of a tangent line at a particular point, and we're just told here's the value at 2. So a is 2. So f prime of 2, yes, that's how you read that, f prime of 2 is the limit as h approaches 0 of f of 2 plus h minus f of 2 all divided by h. So now you're going to take this value for 2 and we're going to substitute it into our lovely equation. After, of course, you take 2 plus h. So 5 times x squared becomes 5 times 2 plus h squared. Plus 3 times x becomes plus 3 times 2 plus h minus 1. And then we have to subtract f of 2. So minus, substitute 2 in place of x. Okay, we're going to have to FOIL this out and distribute. Here we're going to distribute, and then we're going to look for like terms. So 20 plus 20h plus 5h squared plus 6 plus 3h minus 1. So that's all from our 2 plus h minus, well, f of 2 turned out to be 25. Again, combine like terms. 20, the constants, 20 plus 6 minus 1 minus 25. Hey, what do you know? Turns out to be 0. Combine the h's, 20 and 3, that's 23, plus 5h squared. And as expected, h is a common factor. Factor, simplify, reduce. So this becomes the limit as h approaches 0 of 23 plus 5h. If we substitute 0 in place of h, this simply becomes 23. So there's our answer. Okay, again, they asked you to find the derivative of the function, blah, 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 at the number 2, and your answer is 23. Find the derivative of this function at this point, at this value. Your answer should be a single number. Okay? Now, find the derivative again, but note here difference between part A and part B. Here's our new function, f of x is, ooh, yay, square root of x. We love dealing with square roots, don't we? Find f prime of a. So for the first part here, now compare that part B, f prime of 1, f prime of 4, f prime of 9. We're going to, in part A, come up with a formula. Okay, we're using a variable, not a specific value. Once we get that formula for part A, then B is just going to be a pretty simple substitution. Okay, so let's deal with the formula from part A. So again, they keep writing out the definition of a derivative, so you get used to seeing that. The limit as h approaches 0 of f of a plus h minus f of a divided by h. So our function in this case, f of x, is square root of x. So f of a plus h becomes square root of a plus h minus square root of a over h. And what do you do to simplify that? Nah. You can't factor anything out. Can't reduce. I'm sorry. What did you say, Kate? Absolutely. We use the conjugate. Take your time, write it out, be careful, good penmanship. Square root of a plus h minus square root of a times square root of a plus h plus square root of a. Multiply top and denominator. Now again, leave your denominator in its factored form. There's no need to distribute and make that even messier than it is. And we multiplied top and bottom by the conjugate so we could get rid of all those pesky square roots in the numerator. So square root of a plus h times square root of a plus h will give us a plus h. Outside, inside products, those cancel out. Negative square root of a times positive square root of a gives us negative a. Oh, would you look at that? A and negative a, those combine to give us 0. So my numerator simply becomes h. Oh, then we can reduce, and now it's 1 over square root of a plus h plus square root of a. Are we going to get 0 in the denominator if we substitute 0 in place of h? No, look at this. Square root of a plus 0 is simply square root of a plus square root of a. So there's 2 of those square roots of a. So this then becomes our formula there for the derivative f prime of a. Well, once we've got that, then we can move on to part B and simply substitute into our newly found formula. So much easier. F prime of 1, well, square root of 1 is 1. 1 times 2 is 2, so that is 1/2. F prime of 4, that's 1/4. F prime of 9, that's 1/6. And then they're showing you the visual. Y is equal to square root of x, like a sideways parabola, but just the positive, the top half of it there, showing you at different points along the. It's really hard for me to see that blue parabola. Semi-parabola? Is that what we call that? There's only half of it there. And then the red tangent lines, what we found are the slopes. So the slope of the tangent line at those particular values can be thought of as a way of defining the shape of the curve. But you'll get into that much, much more deeply in the calculus. I'm sorry, this may look like we're abruptly changing the subject, but we're really not. The average rate of change of a function between two values, well, okay, average rate of change, it's kind of slope. Take the change in the y over change in x. Well, how can we tell the change in y? Well, you have to take f of x minus f of a. The change in x is going to be x minus a. That looks so familiar. This is another way that we define a derivative, the instantaneous rate of change. So it's just putting it all together and trying to understand once this idea of the derivative, the limit as h approaches 0, was first published, we have come up with dozens, I am not exaggerating, dozens of applications of that. So here's one of them, okay? Instantaneous velocity. If x is measuring time and f of x or f of t um, is displacement, the instantaneous rate of change becomes the velocity of that object at any instant in time. Instantaneous velocity. For example, we started, quite high, and we've dropped something. If an object is dropped from a height of 3,000 feet, okay, you're not getting on top of your roof to do this. Don't get on top of your roof, that's dangerous. Its distance above the ground, measured in feet, after t amount of time, measured in seconds, is given by, yay, the force of gravity, h of t, the height as a function of time, is 3,000 minus 16t squared. How fast is that thing moving after 4 seconds? Okay, so to find instantaneous velocity, we're going to take the function that they gave us here, this h of t, and we're going to find its derivative and find that value, then add 4. Oh, by the way, so basic substitution in there. H of 4 is 2,744 feet left to go. So instantaneous velocity, we're going to take h of t minus h of 4 over t minus 4. So the way they've got this one set up is we're going back to that first formula version of a derivative. Okay, we're not using the form that has h in this case. We're using the form where x approaches a, or in this case, t approaches 4. So again, remember our function here, h of t was 3,000 minus 16t squared. They've got that off to the right side for you there. So 3,000 minus 16t squared minus f of 4. They said that previously, 2744 over t minus 4. Combine like terms. Oh, look, the numerator not only has a common factor of 16, but then we can factor that down because it's the difference of perfect squares. And now notice here, 4 minus t and the t minus 4 are almost identical. So if we take, say, that numerator and factor out a negative 1, then we can reduce those. But realize we get that negative that wasn't there before. We've eliminated the denominator, so we can go ahead and do the simple substitution. 4 plus 4 is 8 times negative 16. The negative sign indicates that the height is decreasing, and it's picked up speed, and it's now falling at 128 feet per second. All right, that's pretty much it. Again, scroll down to the bottom of the notes. You should be able to find the assignment for you from chapter 13, and then we'll move on from here. Good luck, everybody.